Lesson 8.5, Attributes and Transformations of Cubic Functions. The objective for today is that students will be able to graph and analyze the key attributes of cubic functions and their transformation. Now, this is not the first time we've done something like this. We've done this multiple times. We've done it with the parabola function. We've done it with the square root, and the absolute value and whatnot. So this is not our first rodeo. We have also done with the exponential function. Today we're going to be working with the cubic function. Now, before we begin with today's lesson, I just wanted to go ahead and give you guys the answer for the do now. If you guys have any questions or want me to show you how to do the do now, just, send me a message through the chat and I will go ahead and show you guys how to do that. So we're going to go ahead and we're going to be dealing with the attributes and transformations of cubic functions. Now, to begin this lesson, the parent function for a cubic function is going to be y equals x to the power of 3. Whenever you hear the word cubic, you kind of like relate the word cubic to the number 3, right? So whenever you see cubic, you should always think of the number 3 because that's what we're dealing with. Now, 3 is going to be an exponent, right? So if you look at this right here, I have an exponent of 3. So whenever you're dealing with cubic functions, the x variable is always going to have a power of 3. If it has a power of 2 or anything else besides a 3, it is not going to be a cubic function anymore. So if I were to change that 3 into a 2, it's not going to be called a cubic function anymore. It's going to be called a parabola. Why? Because parabolas have powers of 2. So now that we've established that, we're going to go ahead and we are going to graph this function. Now, the thing here, though, is that we've never graphed a cubic function before, not without knowing what it was. So what we're going to do first is we are going to create a table. Okay, fill out those values. Once we have those values, then we're going to go ahead and we are going to plot it in our coordinate plane over here on the right side. So I already went ahead and pre-selected some values for x. So -2, -1, 0, 1, and 2. Okay, now usually what do we do with these x values? Well, we substitute them in for x right here, right? And then we go ahead and we find the values of y, which is this over here. So I'm going to go ahead and I am going to plug in -2 into x to the power of 3. So I'm going to get -2 raised to the power of 3. Now, remember, whenever you're dealing with negatives, you should always just put parentheses to make sure that you're evaluating the expression properly. So that means that I'm going to have 3 -2's, right? Because it has a power of 3. So that means -2 times -2 times -2. Or the little trick that I taught you, that if you have a negative raised to an odd number, your final answer is always going to be negative. If it's raised to an even number, it's going to be positive, right? So you can have -x squared. It's going to give you a positive x. Why? Because it's an even number. It's also going to, you can say -x to the 4th. It's going to be x squared and then to the 4th. You can also do -x to the 3rd, but because that's odd, it's going to be negative, right? And then -x to another odd number, 7, it's going to be negative. So just keep that in mind. So now here, I know that that's odd, so it's going to be a negative times a positive times a negative is a negative. And then 2 times 2 is 4, times 2 is going to be -8. And then we continue the process here. So I'm going to have a -1 cubed, which means -1 times -1 times -1, which, oops, I don't know what happened there. Which is going to equal to a negative number, and then anything times just itself, 1, 1, 1, is just going to be 1. Here we're going to get 0 cubed. Now, I don't need to put the parentheses anymore because that 0 is just neutral. It's not negative. 0 times itself, no matter how many times, it's just going to be 0. 1 cubed right here is literally just going to be 1. And then 2 cubed is literally just going to be 2 times 2 times 2, which is literally going to be the same thing as the first one. So it's just going to be 8, but instead of being negative, it is going to be positive. So now that I have that, my ordered pairs are going to be -2, comma, -8, -1, comma, -1, 0, comma, 0, 1, comma, 1, and then 2, comma, 8. So now what I'm gonna do is I'm gonna get these ordered pairs, and I'm gonna go ahead and I am going to graph them. Okay, so we're gonna start with the first one, which is this one right here. Okay, I'm gonna graph it. -2, comma, -8. 1, -2, comma, -8. 1, oops. 1, 2, 3, 4, 5, 6, 7, 8. -8. So that's my first point. Okay, second one is going to be -1, comma, -1. That's my second point. And then I'm going to get 0, comma, 0. Third point, 1, comma, 1. Fourth point, and then 2, comma, 8, 2. 1, 2, 3, 4, 5, 6, 7, 8. 2, comma, 8. That is my fifth and final point. I'm going to go ahead and color coordinate them just to kind of like visualize it, and because we can, you know, technology helping us out over here. Just so you guys can kind of like match where these come from and see why I plotted them where I plotted them, because X, comma, Y. So now that I've done that, I'm going to go ahead and I'm going to connect the dots. Okay, now have we seen this function before? Yes, I've actually used it in previous examples. This is the one that I would talk about, that it kind of looks like a double helix, well, half of a double helix, or it looks like an X chromosome, or the half of an X chromosome, or, you know, just like an X, right? If I were to, let's say, draw the other half of this, right? If I were to do the other half, it would look something like that. And then you could see where I get the double helix from. So that's what this function is going to look like here. I'm going to go ahead and erase that because we don't need that. Okay, now with every function comes key attributes, right? Well, what is the first key attribute we always talk about in class? Well, you guys guessed it, the domain. So the first thing we're going to talk about here is going to be the domain. And if you guys remember, the domain goes from left to right. So I am going to go ahead and I am going to put my pencil on my paper and just go from left. And if I go from left to right, the first thing that I touch, okay, is this, right? And whenever we see an arrow, arrows always represent infinities. Now it is on the negative side. So this is going to be negative infinity. It is also an arrow, so I'm going to use parentheses. And then I'm going to go all the way over to the right side, follow the function, and now I'm over here. Now it's on the right side of the graph, so this one's going to be a positive infinity. So the domain for the cubic function is going to be from negative infinity all the way up to positive infinity, or you guys can say all real numbers. Okay, now the next one after domain would obviously be range. Range goes from the bottom to the top, where the bottom is negative infinity and the top half is positive infinity. Seeing that the arrow is going downwards, I'm going to say that my range is negative infinity, and it goes all the way up to the very top, which is now going to be positive infinity, or all real numbers. Now this function, if you notice, is also intersecting with the x and the y axis. So this function has an x-intercept and it also has a y-intercept. Now the x-intercept, to our convenience, is when it crosses the x-axis. Just, to kind of refresh your memory with that. Or touches the x-axis. And in this situation, it's perfect because it is crossing at the origin, which is going to be the ordered pair of 0, 0. Now, the next one that we have is the y-intercept. Okay. Now, the y-intercept is the same thing as the x-intercept, except that we want it with the x-axis. So this one can cross or touch the y-axis. Okay, and to our convenience, this is also going to be at 0, 0. Now, the last and final thing that we're going to talk about is something called a rotational symmetry. Okay, now what is a rotational symmetry? Okay, rotational symmetry is a shape. A shape has rotational symmetry when it still looks the same after some rotation. So if I were to rotate, let's say this half of the function, like let's say a couple of degrees, it would look exactly like this half over here. And so that's kind of when you have rotational symmetry. Okay, now the point at which you can rotate it to make it look the same in this situation is also going to be our origin, right? So this point right here, okay, is going to be our rotational symmetry. Which, again, for this situation, since there are no transformations, happens to be at the origin 0, 0. Is it always going to be at the origin? No, it just happens that in this parent function, it is. Okay, so now we're going to go ahead and we're kind of going to, describe the transformations and learn how to graph these functions without a calculator. And we are going to be using the equation that you see right now. Have we seen this equation format before? Yes. Should not be different. The only thing that's going to be different is the fact that now we have a power of 3, which means that when I graph it, I need to make sure that I am creating this shape right here. Okay, so I'm going to go ahead and just give you this information and make sure you guys are copying it down in your notebook. And then we can go ahead and just quickly talk about it and head into the graphing part. Okay, so here we have a negative, right? We have a parentheses b x minus h parentheses power of 3 plus k. The negative in front of the a in red basically represents a reflection over the x-axis, which means that now it's going to look a little bit different from the original function that I just graphed on the previous page. So whenever you do a reflection over the x-axis, is that going to change the way the function looks? No, but it is just going to flip it the way that you see right here. Okay, so this one's flipped from the way that I drew it in the previous one. A is going to represent vertical stretching or compressing, whereas the B that's inside of the parentheses in front of the X, this one right here, is going to represent horizontal stretching or compressing. So the vertical stretching is going to be when the value of A is greater than 1, and vertical compression is when the value of A is between 0 and 1. Okay, now the B, which is going to represent horizontal stretching or compressing. And the stretching is going to be the opposite of the vertical one. It's actually going to be between 0 and 1, whereas the horizontal compression is going to be greater than 1. Okay, and so then we go ahead and continue to H. Now, do notice, like, what is going to be the difference between H and K is that the H, you can find it inside of the parentheses, and the K is always going to be on the outside. Okay, K will always be outside of parentheses. Okay, so H is going to give us a shifting left or right. If you have a positive H, you're going to go left. And if you have a negative H, you're going to go right. So just kind of remember to always do the opposite. Okay, you always want to do the opposite for H. Now, are you going to do the opposite for K? No, you are not. You only do that for H. Okay, for K, you're either going to shift up or down. If it's a positive K, you go up. If it's a negative K, you go down. Okay, all of this stuff we've seen before, should not be new. With that being said, we're going to go ahead and use all of this information to help us graph our equations just by looking at the equation without having to use any calculator. Now, later on, if you guys want to use a calculator to double check that what you guys are doing is correct, be my guest, but you should be able to just, kind of like give a rough a sketch of the graph just by looking at the values in the equation and this information on this page. Okay, so now we're going to go ahead and move on to the graphing. Okay, I'm going to go ahead and write some examples and then we'll go ahead and talk about it together. Okay, so these are the 4 examples that I have for now. We want to identify the transformations for the given functions and provide a graph with this as well. So there are a couple of differences. First off, here, this one is a +2, whereas this one right here is a -2. I also have a +2 here and a -2 here, but the difference between 1 and 2 and 3 and 4 is that 3 and 4 have parentheses, whereas the first 2 don't. So since these two do not, since 1 and 2 don't have parentheses, that means that this +2 and this -2 are going to be the value of K. Okay, that means that this right here is K. And K, according to the previous page, says that I go up or down. So this means right here that I'm going to go up 2. Over here, I'm going to go down 2. Since these right here, 3 and 4 are in parentheses, this means that this right here is H, and I have to do the opposite of H, which means that instead of going to the right by 2, I'm actually going to go to the left by 2. And over here, I'm actually going to go to the right by 2, because I always have to do the opposite for H. So now that I have that, I can easily go ahead and create these functions. Now, just a little heads up. Whenever you're doing this, whenever you're graphing these types of functions, okay, the starting point is going to be at 0, 0, which is the origin. So just keep that in mind as you guys are doing this right here. Okay, my starting point is going to be 0, 0. So as I graph these, okay, my starting point is always going to be at 0. And then from 0, I go ahead and do the transformations. So my starting point is 0, and now I'm going to go up 2. So I'm going to go 1, 2. My new point is there, and I'm going to make sure that when I graph this, my rotational symmetry is right there, okay? So this right here is going to be my rotational symmetry, meaning that that is the point at which the function rotates. So when I graph it, I'm just going to do this, connect it there, and then go upwards and change the direction in which it goes. And that right there is a quick sketch of the function. I do the same thing here. Start at the origin, 0, 0. And now I'm going to go down 2. So I'm going to go 1, 2. And now I'm at that point. So that right there is my rotational symmetry. Okay. RS. So now I'm going to go ahead and graph this function. I start going downwards, going up, connect it there. And now that I'm at the rotational symmetry, I change the direction and make it go upwards. Okay. Now we go to number 3. Starting point is 0, 0. I'm going to go to the left by 2. So I'm going to go 1, 2. That's my new point. Now that point becomes my rotational symmetry. Okay, so I'm going to go downwards, up, connect it there, rotate, and make it change directions. And that's what I got. Have the next one. I'm going to go to the right by 2, starting at the origin, 1, 2. That's my new rotational symmetry. So now I go from the bottom to the rotational symmetry, meet at the rotational symmetry, and then make it go upwards. And that right there is kind of like how you graph these functions and identify the transformations. Now we move on to more examples. Okay, more examples. Okay, so these right here are our next examples. Now, do notice there are a couple of differences. Here, this 2 is in front of x, and so is this one. But this is not a 2, that's a fraction. Same thing here, whole number fraction. The difference between 5 and 6 versus 7 and 8 is that this right here has parentheses. So that means that these right here are going to be horizontal compressions and stretchings. We just have to figure out which one's vertical and which one's horizontal. If you remember from the page, the second page is that the number in front of the x without parentheses is going to be the vertical. So this right here is going to be A. Okay. And this one right here is going to be B. Now, how do I know between A and B? Well, A is outside of the parentheses or has no parentheses versus B, which does. Okay. Now, if it is a whole number, that means that this one right here is going to be a vertical stretching by a factor of 2. Whereas the other one, because it's a half between 0 and 1, it's going to be a vertical compression by a factor of a half. And this one right here, remember they're the opposite. So that means that this right here is going to be a horizontal compression by a factor of a half, because I don't know if you guys remember, for horizontal compression and horizontal stretching, you have to do the reciprocal. Okay, so that means that if it's a 2, it's actually not a 2 because you have to flip it to give you 1/2. Okay, so it's a horizontal compression by a factor of a half, and this one over here is going to be a horizontal stretch by not a half, but by 2, because the reciprocal of a half would be 2. So now I'm going to go ahead and graph these in decimals. Go ahead and copy paste them on here so that way you guys can see the actual, a closer accurate image of what the horizontal and vertical compression and stretching look like. Okay, I went ahead and provided the graphs right here. I know I probably should have chosen a different number, but I went ahead and provided both of the graphs. So if you look at this here, we have this, the one showing vertical compression here in red. Oops, my bad. Vertical compression is going to be here in red. And the vertical stretching, I'm going to go ahead and put it right here in green. Okay, so you have that one right there. And I also went ahead and labeled them right there. You do see a big a difference. So the vertical stretching is just going to be increasing at a faster rate, which means right here that it's going to be increasing faster, versus the vertical compression is going to be increasing at a slower rate when compared to the vertical stretch. So that's kind of what's going to happen there. So one of them is going to be, if you want to use like different terms, it's going to be thinner, whereas the open up is the other one, vertical compression, is going to open up a lot wider. So we go ahead and we do that for horizontal stretching and compressing. Okay, so now we're going to go ahead and we're going to continue with these right here. So I went ahead and just graphed it on Desmos. So the 1/2, it's a little bit more drastic with the horizontal compression and stretching. But here, the horizontal stretching is actually going to be the black line right here. So when I graph it, I want to go ahead and kind of like exaggerate it a little bit. It's going to be opened up a lot wider, whereas the vertical compression is actually going to be opened up a lot thinner. So just, keep that in mind when you guys are creating these graphs. So with that being said, I'm going to have like maybe 2 more examples with a little bit like all of these mixed in together. And then I will go ahead and give you guys your homework. So let's go ahead and continue. Okay, so these are the examples that I'm going to give you. I'm going to go ahead and start by identifying the transformations, by stating that this negative right here is going to be a reflection over the x-axis. Okay. And now this 5, because it's outside in front, is going to be A, meaning that it is going to be a vertical stretch by a factor of 5, because that 5 is greater than 1. This -6 is going to be H, meaning that the +3 that is on the outside is going to be K. So that means that the H, because it's negative, is actually going to tell me to go to the right by 5, and that +3 is going to tell me to go up by 3. I'm going to go ahead and graph these, and then just remember to always begin at the origin of 0, 0. Okay, so I'm going to go to 0, 0. Okay, and I'm going to go ahead and I'm going to go to the right by 5. 1, 2, 3, 4, 5. Okay, and then check mark there. I'm going to go up by 3. 1, 2, 3. So that right there is my rotational symmetry. Now, if we look back to the examples that we have here, a vertical stretch by 5, well, what does that mean? Is it going to be open up wide, or is it going to be thin? So we have to go check it out again to kind of refresh our memories. Vertical stretch means that it's going to be thin, right? According to this, it's going to be thin compared to a vertical compression. So when I graph this, remember, this is just a sketch. I'm going to go ahead and I'm going to make it thin. Okay, so that's what that means right there. But a reflection over the x-axis means that it's going to be the opposite of what we had up here. So instead of going like this, it's going to be the other half of the graph, which we said would go something like that. Okay, so I'm going to go ahead and graph that over here, and just make sure that my line is thin, more stretching rather than compressing, and it has to happen at the rotational symmetry right here. Okay, so that means that my graph would go something like this. You can always just double check it by graphing. So now we're going to go to problem number 10. We have 3/2 with here. Now, over here, this 3/2 is inside the parentheses, so that means it's not going to be vertical. This one is going to be a horizontal. Okay, now remember, you have to do the reciprocal of 3/2, so that means that it's going to be a 2/3. So that means that is going to be a horizontal compression by 2/3. Okay, that plus 1 here is h, and then that minus 5 is k. So that h tells me to go 1 to the left, and then that minus 5 tells me to go 5 units down. And when I do this, remember, once again, start at the origin. So I'm going to go ahead and I'm going to start at 0, 0. I'm going to go 1 unit to the left, and then I'm going to go 5 units down. 1, 2, 3, 4, 5. So then that goes down over here. And that right there is going to be my rotational symmetry. Now, do I have a reflection over the x-axis here? No. So is it going to look like the one that I have over here? Nope. It's going to look like the regular one that we graphed at the very, 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 very beginning of this lesson. But I do have a horizontal compression. What does that mean? Well, let's kind of refresh our memory here. A horizontal compression means that it is going to look like the purple one here. So once again, it's going to look very thin. Okay, so let's go back over here, make this one look very thin. Oops. And that right there is today's lesson. I'm going to go ahead